All right, this is unit number 15, Geometric Optics. The first part of this unit is going to be a little review, and in that review we're going to mix in a little bit of some new stuff. So we're going to take a look at the first part here. Diffraction we've talked about, reflection we've talked about, and at the bottom refraction. So I'm just going to do a quick review of diffraction, take a look at reflection, quick review, talk about the law of reflection. That'll be kind of new, and then we'll hit the law of we'll talk about refraction, and then the rest of this is on refraction. So we'll start off with the beginning, and this is going to be on diffraction. So here it is. So diffraction, we talked about this last chapter, is the bending of a wave around a barrier. Okay, and one of the best examples of that is if you have a single slit and you have waves coming in. Those waves are going to bend around. Okay, and if you didn't diffract, those waves would go straight through like this, and you would get nothing, no wave on the sides. And since waves do diffract, you'll get that bending around effect, and so that should be pretty much straightforward there. And we've talked about that. All right, the wave does not change mediums. Okay, so when we talk about diffraction, we're not going from one medium to another. We're staying in the same medium. So if this were water, it would be water over here, and then water over here. If this were light waves coming in, it'd be light waves in air, and then over here it'd be light waves in air. So the medium doesn't change. Okay, the next one, reflection. We've talked about this. This is the bouncing. Bouncing back of a particle or that strikes the boundary between two mediums or two media. And so on this one we have this. So reflection is like an echo. It's like you seeing yourself in a mirror. Those are pretty straightforward. Alright, so law of reflection. This is when light reflects from a surface, the angle of incidence and the angle of reflection are equal. Alright, so what does all of that mean? Alright, so let's just imagine we have like a surface down here. Let's say that it's like a mirror. So it'd be a flat surface, and I'm going to get a ruler out. Let's see if I can make this do a little better job at this. So I've got a mirror here, and then I take like a laser, and I shine the laser on that mirror. Alright, now when we talk about what's called the angle of incidence and the angle of reflection, what we need to do is, as soon as we find where that light ray intersects the mirror at, just draw on a normal line. Remember, a normal is going to be perpendicular, okay, perpendicular to the surface, and this angle right here, that's theta I, the angle of incidence, like incoming. Alright, once it hits, it'll bounce back off, and when it bounces off, it'll bounce off in what's called the reflected ray. So this is the incident ray, okay, and this is the reflected ray. Alright, and what we find out is every time that we have a reflection, the angle of incidence and the angle of reflection, so that's theta R, those two are always the same. So theta I and theta R are always the same, and that's all that means. And that's the law of reflection. Alright, and we'll come back and use that a little later on. So if we're looking to define things, this is I and this is R. And this is the angle between the incident ray, which is this guy, and the normal. And the reflected ray is the angle between the reflected ray, which is this guy, and the normal as well. So they're always based upon, or always drawn from, the normal, not the surface. And that's just something you just got to kind of keep in mind as you go through this stuff. Okay, so we did diffraction, we did reflection. There's the law of reflection. Now we're going to go to our third term. We talked about this third term earlier, and this is refraction. And this is a lot of this chapter is on refraction. All right, and this is the bending of a wave when the wave moves from one medium to another medium. So we switch media. And so anytime you switch media, you're basically talking about refraction. So let me give you an example, or just kind of a little quick thought on this. So let's say you have a barrier, and I have one medium here, another medium here. Maybe it might be like air up here, alright, and then water down here. So you're above the water here in the air, and then you're below the surface of the water down here. And if you take a laser, right, and you aim that laser at that water, normally we would probably predict, that laser is going to keep going straight, okay, and never bend. But it does bend. When you go from one medium to another, and you switch mediums, what happens is that ray will bend. Now how it bends, and that was probably not real good on my part, how much it bends is what we're going to talk about in just a moment. But we just need to know that the fact that it does bend. And so it doesn't stay the same direction, it does change. Alright, and we want to know how much it bends. And to figure out how much it bends, we always measure it, just like we did up here. We measure it off of the normal. And so we're going to call this is going to be theta I, okay, like the incident angle. And then this will be theta R, like the refracted angle. You'll also see this is theta 1. And this guy down here is theta 2. So you'll see theta 1 and theta 2. You just need to remember that theta 1 is the incoming, the incident ray, and theta 2 is the outcoming, or the refracted ray. Okay, the next one. Okay, so let's kind of put all that together. So we have the incident angle, and we'll put our thetas on there. Remember we said we can call this theta 1 or theta 2, theta 1 or I. I'll call I, and we'll call this R. Alright, it's the angle between the incident ray and we've been through this, the normal. So it's the same definition as the other ones were with the angle of reflection. So we have refracted angle, the angle between the refracted ray and the normal. Okay, we'll watch this video when we come back to class. When a wave refracts, there's some things that occur. The speed of the wave will change. So you have some things that stay the same. Actually, you have one thing that stays the same. And you have a bunch of things about the wave that are going to change. And we're going to talk about what those are. Alright, here it is. When light leaves a vacuum, alright, so leaves a vacuum, it will slow down. And you can kind of remember this by just thinking that light travels fastest in a vacuum. So if it travels fastest in a vacuum, then when it leaves the vacuum, it's got to be traveling slower, so it's going to slow down. And when it enters a vacuum, it speeds up. And so if we were to go back to this example that we had just a little while ago, the speed, if this were air, and the speed in water, actually the speeds, it'll actually slow down. Because in water, which is more optically dense, it's going to travel a little bit slower than it will in air. Alright, moving on. The amount light slows down, so how much it slows down when it leaves a vacuum depends upon what's called the index of refraction. That's a big concept that we're going to use all chapter. Okay, it's called the index of refraction. And I really need to put a abbreviation in here because we didn't talk about that. So if you want to slide in an abbreviation, the abbreviation for the index of refraction is N. Doesn't that make sense? But that's what we use. Alright, so here it is. The index of refraction is this. It's a ratio. Okay, when we think about ratio, we want to think about a fraction. So here's N. Okay, here it is. It's the ratio of the speed of light in a vacuum to the speed of light in a given medium. Okay, so if we kind of push this all the way out, so speed of light, the abbreviation for that in a vacuum is C. Speed of light in a medium is V. So the index of refraction, the equation for it, is just a ratio. It's going to be C divided by V. And if we take a look at the units on this, C is it's a rate, it's a speed. So that'll be meters per second, and V is meters per second, and you can cancel all that out, and so N then is unit less. Alright, let's go back up here real quick and define this, and then we'll go ahead and include index of refraction onto our unit sheet. So ratio, it's the ratio of the speed of light in a vacuum to the speed of light in a given medium. Alright, so why don't you take a moment, if you need to stop the video, stop it, and go ahead and add index of refraction to your unit sheets. And it has no units, so it makes it pretty darn simple. Okay, moving on. The index of refraction for a vacuum is defined to be, okay, now let's think about this. If we go back up here, if we're talking about light traveling in a vacuum, that's going to be, this v here is going to be the speed of light in that particular medium. Well, I know vacuum is really not a medium, but it's a place that light would be traveling. And so the speed of light in a vacuum is going to be c. And so if those will cancel out, and that'll be 1. So the index of refraction in a vacuum for light is 1. So if we go down here, the index of refraction for a vacuum is defined to be 1. It's an easy one. All right, now we need to figure out what the index of refraction is for air. And what's interesting about it, air comes up to be really, really close to 1. It's not exactly 1, but it's really, really close. And so to make life easy, we'll say that the index of refraction is 1. Okay, and this will be helpful on homework and problem set questions. So unless otherwise stated, treat air as having an index of refraction of 1. All right, and if you look down here, here's our table. So vacuum is 1, exactly, that's the way it's defined. Air is really close to 1. But we accept it. It's actually a little bit more than 1, but we accept it to be 1. Just makes it a little bit easy. It just makes it easier that way. And then there's the index of refractions for the rest of them. Notice diamond has an enormous index of refraction, which is what gives diamond its real sparkly, shiny type of appearance. All right, let's move on. Okay, so if the speed of light changes as it enters a new medium, we just talked about that. How is the frequency and wavelength affected? Well, we can use our wave equation to answer this one pretty quick. All right, so we know that let's say the speed goes down. So it slows down as it goes from air into water. Then something over here has to change. And what we find that changes is the wavelength. The wavelength will actually shrink a little bit. And it'll allow us to keep the frequency the same. So frequency stays the same. That's kind of an important thing to kind of remember when you're dealing with light. So generally speaking, frequency is used to identify the type of light. So when the speed is reduced, so is the wavelength. All right? Wavelength or the frequency will change if you're talking about the Doppler shift. So that's kind of different. But if you're just going from one medium to another, frequency will stay the same, and the speed and the wavelength will move together to keep the frequency the same. All right, and then we come across what's called Snell's law, and Snell's law is kind of like the big three of light. It's actually one equation, but it's a real important one, and it's named after a Dutch physicist, okay, who lived from 1580 to 1626, and again, you don't have to have those memorized, but I'm just kind of throwing it out there so you can get some perspective. And let me kind of show you what's going on with this. So we'll do a quick diagram, and here's our two media. So let's say this is going to be media 1 and media 2. We'll have a laser come in, so there's a laser light. We'll draw on the normal. I'm having a hard time drawing this with a staple in this. Here it is. So here's the normal. And if medium 2 is more optically dense than 1, what does that mean? It means that n here is going to be small and n here is going to be real big. Then what will happen is this light, when it goes through, will actually bend towards the normal. And so this is going to be theta 1. This is theta 2. Here's the incident angle. Here's the refracted angle. We can also call this theta I and theta R as well. All right, so with that setup, here is Snell's law. When you first learn Snell's law, typically they'll make it look like this, but we're going to modify it here in just a moment. So when you first see Snell's law, it looks like this, where this is theta 1, this is theta 2, this is the speed of 1, and this is the speed of 2. All right, but on the side, we're going to modify this a little bit. We know the equation for the index of refraction. That's going to be C over V. I'm going to rearrange it and get V equals C over N. C will never change. That's always going to be the same. But these two will move together. So if this is the speed of that light in a particular medium, this will be the index of refraction for that particular medium. So these wands are going to match. So if it was V2, it just would be simply C over N2 as well. And what I'm going to do is I'm just going to make this substitution right here in for these guys. So I get sine of theta 1 over sine of theta 2. And then I'm going to do the substitution. So I get C over N1 over C over N2. And then you can easily see, well, I'll show the extra step. So I get sine of theta 1 over sine theta 2. And if I invert and multiply, everything go well, girls? Okay, you guys are now on the official tape here. All right, your C's will cancel out, and then you're left with an expression for Snell's law that is the more common way. So I'm going to basically cross multiply. So I'm going to multiply through here. So I get N1 sine theta, actually it'd be N2, equals N1 sine theta 1. And that's how you're usually going to see Snell's law. And we'll use this and an aquarium, a protractor, and laser to answer a bunch of questions tomorrow. See you tomorrow.